Hey everyone, ready for another deep dive? This time we're tackling thermodynamics.
A fascinating subject indeed.
You sent over some excerpts. They look like, well, pretty intense.
Textbook stuff, yes, but foundational. The core ideas of heat and how it works.
Okay, good. I mean, it starts out pretty simple. Putting ice cream in the freezer, I can handle that. But then it throws this zeroth law of thermodynamics at us. Sounds intimidating.
It does, doesn't it? But it's simpler than it sounds. Think of it like the rule that lets us even talk about temperature, like what it means.
Okay, so is it saying that if the ice cream is the same temperature as the freezer air, and my frozen peas are too, then the ice cream and peas are also the same temperature? Seems kind of obvious.
Exactly. We just take it for granted, but that's the Zeroth law in action, and that's what makes thermometers possible.
Huh. I never thought of it that way. Thermometers. Just there, telling us how hot or cold things are. So the source mentions all these different types of thermometers, though. Constant volume gas, constant pressure gas, mercury. Do those all work the same way?
At their core, yes. They all rely on thermal expansion. Things get bigger or smaller when their temperature changes.
Ah, like the mercury going up the tube because it expands more than the glass when it gets hotter. So anything that changes reliably with temperature could be a thermometer, theoretically. Like, could you use cricket chirps? I swear they chirp faster when it's warm.
That's the right idea. If you could precisely link chirps per minute to the actual temperature, you'd have a cricket thermometer. But practically speaking, mercury or gases are more reliable.
Makes sense. So there's also this triple point thing the source mentions. What's so special about the triple point of water?
Well, that's where water can exist as ice, liquid, and steam at the same time.
Hmm.
Very specific temperature and pressure,
Like a magic trick?
in a way. But it's super precise and repeatable, so much so we use it to define temperature scales to make sure all our thermometers are actually accurate.
So it's like the gold standard. Makes sense. Okay, back to thermal expansion for a sec. The source talks about how a pendulum clock slows down in hot weather. Is that really a thing?
Absolutely. A pendulum swing time depends on its length, right? When things heat up, they expand. Longer pendulum, slower swing.
That's why my grandpa's old clock was always off in the summer. I thought it was just old. But it's physics. So this expansion thing affects more than just clocks, right?
Oh, definitely. Bridges, power lines. Engineers have to factor it in constantly. Imagine a bridge designed without considering that steel expands in the heat. Disaster waiting to happen.
Wow. It's like this invisible force shaping the world around us. And the source mentions these coefficients of expansion to linear and volume. Those are like measurements of how much things expand.
Precisely. Linear is for length, volume is for, well, volume. Different for each material, that's why some things expand more dramatically than others.
So like concrete and steel are different, which matters when you're building things, I'm guessing.
Huge implications. Ensures buildings don't crack, bridges don't buckle. Knowing those coefficients is essential for making things work in the real world.
This is making me look at the world totally differently.
Okay, one more thing for now. Calorimetry. It sounds kind of like the detective work of heat, right?
That's a great way to put it. It's about measuring heat transfer, like when you pour hot tea into a cold cup.
Okay, that I can visualize. But how do you actually measure that exchange of heat?
Well, each substance has something called specific heat capacity. Tells you how much energy it takes to raise its temperature. Plus, you have latent heat, which is about the energy needed for phase changes, like melting ice, boiling water, stuff like that.
So latent heat is like the behind-the-scenes energy for transforming stuff without changing the temperature. That's wild.
It is, isn't it? Think of ice melting. Stays at 0 degrees Celsius the whole time, but it takes a lot of energy to break those bombs and make it liquid. That's latent heat in action.
My mind is officially blown. And to think, this is just the beginning of our dive into thermodynamics.
And we're just getting started. This next part gets into some serious calorimetry action, building on that idea of heat flowing from hot to cold. Yeah, like how my coffee seems to go cold way too fast no matter what.
Yeah.
But how do you actually put numbers to that heat transfer, like measure it?
That's where those specific heat capacity and latent heat come in. They tell us how much energy is involved in those temperature changes and when stuff changes state.
Right, right. One's for raising the temperature, the other's for like solid to liquid, that sort of thing.
Got it. And the source is this great example. Picture this. You've got a glass cup, regular size, at room temperature, like 25 degrees Celsius.
Okay, I'm picturing it. Got my cup.
Now you pour in, say, 200 cubic centimeters of steaming hot tea, like 95 degrees Celsius. What happens?
Well, the tea cools down, the cup warms up, and eventually they meet somewhere in the middle, temperature-wise. But how do you figure out what that temperature is?
That's where the fun begins. We know the specific heat capacities for water, because tea's mostly water, and for glass. Water's 486 joules per kilogram per degree Celsius. Glass is about 840.
So those numbers tell us how much energy it takes to change their temperature. Can we use that to, like, track the heat going back and forth?
Absolutely. The heat the tea loses has to equal the heat the cup gains, assuming nothing escapes to the surroundings. Perfect energy balance.
Okay, so you calculate the heat loss for the tea using its mass, specific heat, and how much its temperature changes. Same for the cup, but for heat gained, right?
Exactly. Then you set those two things equal to each other, and bam, you can solve for the final temperature of the whole teacup system. Bit of algebra, but it works.
It's like having a secret formula for heat. Okay, but the source doesn't stop there. It gets into calorimetry with phase changes too. That's where it gets really interesting.
It does. There's this example. It's like a puzzle. You start with 200 grams of ice and water, all at 0 degrees Celsius.
Okay, ice water. Got it.
Now add 30 grams of steam, superheated to 100 degrees Celsius. The question is, what's the final temperature and how much water do you end up with?
Whoa, that's a lot going on. Ice melting, steam condensing, temperatures going all over the place. How do you even begin to solve that?
Break it down, step by step. Account for the energy in each change. First, you've got the heat needed to melt the ice. That's where the latent heat of fusion comes in. 3.36 times 10 to the 5th joules per kilogram for ice.
So that's the energy to turn the ice to water, but still at 0 degrees, right?
Exactly. Then there's the heat the steam loses as it condenses back into water at 100 degrees. Latent heat of condensation there, it's a big one, 22.5 times 10 to the 5th joules per kilogram.
Wow, a lot of energy. Okay, so then what? We still got temperatures to deal with.
Right. The steam, now water at 100 degrees, it'll cool down. And the original ice water, now all water at 0 degrees, it'll warm up.
So we use the specific heats again to figure out the energy for those changes. It's like weaving it all together.
That's the key. All the heat lost by the steam has to be gained by the ice and water. Perfect balance.
It's mind-blowing how you can break it down like that and make sense of it.
Yeah.
Okay, now the source switches gears a bit, going back to the microscopic world. It mentions this thing called the Maxwell-Boltzmann distribution.
Ah, yes, that's a big one in statistical mechanics. It's all about how the speeds of those gas molecules are spread out at a specific temperature.
Wait, so even though the average energy of the molecules is linked to temperature, they're not all moving at the same speed?
Nope. That's what the Maxwell-Boltzmann distribution is all about. It's like a bell curve. Some molecules are faster, some are slower, but it follows a pattern.
So it's like a bell curve, with the most likely speed right at the peak of the curve.
You got it. And here's the interesting part. The shape of that curve changes with temperature. Higher the temperature, the curve shifts to the right, meaning more molecules are zipping around at faster speeds.
Makes sense. It's like when you heat up a pot of soup, those molecules are getting more energetic and bouncing around faster, hence the delicious aroma wafting through the kitchen.
Exactly. Understanding that distribution of speeds is crucial for explaining so many things, from how gases spread out, diffuse, to how chemical reactions happen.
It's like we're getting a glimpse into this hidden world of molecules and how they're constantly in motion. Speaking of molecular motion, the source also mentions this mean free path thing. What's that all about?
Think of it like this. The mean free path is the average distance a molecule travels before it bumps into another molecule. It's a measure of how much space it has to roam freely before colliding.
So it's like how crowded the dance floor is for these molecules.
Yeah.
The denser the gas, the more crowded it is, and the shorter the mean free path.
Right. And the opposite is true too. In a less dense gas, those molecules have more space to move around, so the mean free path is longer.
It's fascinating to think about all these collisions happening constantly at the molecular level.
Yeah.
It makes you realize how much is going on beneath the surface of things we take for granted, like the air we breathe. But for now, let's shift gears back to heat transfer. The source goes into more detail about conduction. What are the main takeaways there?
Well, as we talked about earlier, conduction is all about heat transfer through direct contact. And the rate of that transfer, well, it depends on a few key things. The temperature difference between the objects, the area where they're touching, how far the heat has to travel, and something called thermal conductivity.
Okay, so if I want to stay warm on a chilly day, a thick sweater works better than a thin one because the thicker material is slowing down the heat escaping from my body.
Exactly. The rate of heat flow is inversely proportional to the distance. Thicker material means more resistance to that flow. That's why insulation is so important in houses and stuff.
So it's all about creating barriers to trap that heat.
Yeah.
Okay, but how do we quantify this relationship between heat flow and all these factors, like mathematically?
Well, there's this thing called Fourier's law. It's a beautiful equation that captures it all. It says that the rate of heat flow, usually written as Q over T, is proportional to the temperature difference, the area, and the thermal conductivity, all divided by the distance.
So if we know all those things, we can actually calculate exactly how much heat is going to flow through a particular material. That's pretty cool.
It is. It's used everywhere, from designing things like heat exchangers to understanding how heat moves through the Earth's crust.
We're really building up our thermodynamic toolbox here. Now, the source brings up thermal resistance. Is that like the opposite of thermal conductivity?
You could say that. Thermal resistance is, well, how much something resists the flow of heat. High conductivity means low resistance, and the other way around.
Two sides of the same coin. Got it.
And just like electrical resistance, you can combine them. Like if you have multiple layers of insulation, you add up their resistances to figure out the total resistance to heat flow.
Like building a heat shield. This is getting more and more interesting. Now, the source gets into this example with concentric spheres. What are those exactly, and why are they important for understanding heat flow?
Picture this. Two spheres, one inside the other, with some material filling the space between them. That's your concentric spheres. They're great for studying heat flow that goes outward from the inner sphere to the outer one.
So it's like heat flowing through the layers of an onion.
Perfect analogy. The trick is figuring out how the heat moves through that shell and how the temperature changes from the inside out.
Sounds complex.
Yeah.
How do you even approach that?
You can imagine breaking down the material into super thin layers, like those onion layers you mentioned. Then, using Fourier's law, you can analyze the heat flow through each layer, considering the temperature difference, the thickness, and the thermal conductivity.
So we're breaking down the big problem into smaller, bite-sized pieces, just like we did with those calorimetry problems.
Exactly. And here's the key. In a steady state where the temperatures aren't changing over time, the heat flow has to be the same through all those layers.
Makes sense. If it wasn't the same, some parts would be getting hotter or colder than others, and it wouldn't be steady anymore. It's like a perfectly balanced flow.
Precisely. And with some fancy math integration, you can get an equation that describes that steady state and how the temperature changes as you move from the center outward.
So it's like a temperature map of the whole sphere. Pretty cool. But the source doesn't stop there. It throws in a twist, a rod, with thermal conductivity that changes with temperature. How does that work?
Ah, that's a fun one. The idea is that the rod's conductivity, usually represented by the letter K, isn't constant. It changes according to a specific formula as the temperature changes along the rod. And the challenge is to figure out how much heat flows through that rod per unit area with this changing conductivity.
Okay, so instead of a constant conductivity, we've got a moving target. Sounds tricky.
It is, but the same principles still apply. Imagine dividing the rod into tiny slices, each with its own temperature and conductivity. You apply Fourier's law to each slice, then put it all together to get the overall heat flow.
Like those onion layers again. But this time, it's a rod. I'm seeing a pattern here. We break it down into small parts, use the laws of thermodynamics, and then put it all back together to get the big picture.
You got it. It's a powerful strategy for tackling these problems. Now, the source introduces another example, a well-insulated rod and a graph showing its temperature distribution. What can we learn from a graph like that?
Well, a graph can show us how the temperature changes along the rod, right? A steeper slope on the graph means a bigger temperature difference, which means faster heat flow.
Exactly. And since the rod is well insulated, we know the heat is only flowing along the length of the rod, not escaping out the sides.
Okay, so the shape of the graph can actually tell us a lot. What if it's a straight line?
Straight line means constant temperature gradient, so the heat flow is constant too.
Makes sense. If it wasn't constant, the graph would be curved because some parts would be heating up or cooling down faster. It's like a visual fingerprint of the heat flow.
Exactly. You can even use the slope of the graph to calculate the thermal conductivity of the rod material. Steeper slope, higher conductivity, meaning heat can flow more easily through it.
So we're literally decoding the language of heat.
Yeah.
It's awesome. Okay, now the source gets a bit more practical with a problem involving a highly conducting cylinder surrounded by insulation. That sounds like something you'd see in real-world engineering, right?
Oh, absolutely. Think of a hot water pipe that you need to insulate to keep the heat from escaping, or an electrical wire that needs protection from overheating.
So we've got this cylinder, maybe made of metal, that conducts heat well, and then it's wrapped in insulation to slow down the heat flow.
You got it. The source sets up a scenario where the temperature outside the insulation is higher than the cylinder's temperature. And the question is, how long does it take for the cylinder to heat up from its initial temperature to some final temperature?
Okay, so we're thinking about how fast the heat goes through that insulation and how much heat energy the cylinder itself can absorb. It's like a race against time.
Exactly. The rate of heat flow through the insulation depends on a few things: the temperature difference, the surface area of the cylinder, how thick the insulation is, and its thermal conductivity.
So a thicker layer of insulation would slow down the heat flow, giving the cylinder more time to absorb the heat and warm up.
Precisely. We also need to consider the cylinder's heat capacity, which tells us how much heat energy it can store as its temperature changes.
Right, heat capacity is like its ability to soak up heat. So we can figure out how much heat it needs to absorb to reach that final temperature.
You're getting it. Then we use the rate of heat flow to figure out how long that transfer takes.
This is so cool. We're breaking down these complex scenarios into steps we can understand. Okay, what's next in our thermodynamic adventure?
The source throws us a curveball with a non-conducting cylinder filled with water and exposed to a cold environment. This one highlights how heat transfer, phase changes, and volume all play together.
Okay, so we've got this container of water right at freezing point, and then it's suddenly in a really cold place below freezing. So it just freezes solid from top to bottom, right?
Not quite. It's more complicated because the water expands as it freezes, which affects the height of the water column.
Wait, so the water level could actually go up even as it's freezing.
Exactly. You've got heat flowing out of the water, causing it to cool and eventually freeze, but then the freezing causes expansion, which pushes the water level up. It's a thermodynamic tug of war.
Okay, this is blowing my mind.
Yeah.
So we've got the rate of heat loss, the freezing process, and the volume change all happening at the same time.
Yep. You have to consider the density of water and ice, how the container's material affects heat flow, and how the volume change translates to the height of the water column.
This is like a thermodynamic ballet. So much going on at once.
It is, isn't it? A great example of how all these different concepts we've been talking about can come together to explain something really interesting. Okay, ready for the next challenge. The source introduces this idea of a lagged stick.
A lagged stick. Never heard of that.
It's just a stick that's insulated along its length so no heat escapes out the sides. Imagine a rod wrapped in a thick layer of insulation.
Okay, I'm picturing it. What happens to this lagged stick?
Well, the source places it between two heat reservoirs, one super hot at 100 degrees Celsius and the other ice cold at 0 degrees.
So one end is getting blasted with heat, the other is freezing, and the heat can only flow along the stick because of the insulation.
Exactly. And the problem is to figure out how the temperature changes along the stick over time. Imagine a heat wave moving through the stick, gradually warming it up from the hot end to the cold end.
I can almost see it, like a gradient of colors from red to blue.
Perfect. To figure it out mathematically, you'd need the stick's properties, like its specific heat capacity and how its mass is distributed along its length. Then you could divide it into thin slices and analyze how the heat flows between those slices, changing their temperatures.
So we could create a movie of the temperature changing throughout the entire stick. This is amazing. Okay, what else is on our thermodynamic agenda?
The source revisits a familiar friend, the cylindrical rod, but this time it's all about melting ice.
Okay, I'm intrigued. What's happening with the rod and the ice?
The rod is connected to a hot steam chamber on one end and ice on the other. As heat flows through the rod, it melts the ice. But here's the twist. The problem introduces a second rod with different dimensions and thermal conductivity and asks us to compare how fast each rod melts the ice. It's like a melting race.
So it's about how the rod's properties affect how quickly it can transfer heat to the ice. Got it. What do we need to know to solve this one?
Well, we'd need the specific dimensions of each rod and their thermal conductivity values. Then we can use Fourier's law again to calculate the rate of heat flow for each rod.
Right, that tells us how much heat energy is hitting the ice every second. More heat flow means faster melting.
Exactly. And to figure out how much ice melts, we use the latent heat of fusion for ice. It all comes together.
This is really making me appreciate how all these concepts are linked. It's like a chain reaction. Okay, what's next?
Let's revisit thermal expansion. We've already seen how it messes with pendulum clocks, but now the source gets into a problem with an aluminum cup filled with a liquid.
Okay, so what happens to the cup and the liquid?
The problem is this: how much liquid spills out? if you heat up both the cup and the liquid. It's like a thermodynamic overflow problem.
Ah, so we need to figure out how much each one expands and if there's enough room in the cup for all that extra liquid.
Exactly. We need those coefficients of expansion again. If the liquid expands more than the cup, you get spillage. If the cup expands more, you've got extra space.
So we have to calculate the volume change for both the cup and the liquid as the temperature goes up. Then the difference between those changes tells us how much overflows, right?
You got it. A perfect example of why thermal expansion matters in everyday design. You don't want your containers leaking or breaking just because the temperature changes. Now, how about we dive into another thermal expansion challenge? This time, it involves a metal rod submerged in mercury.
Ooh, mercury. Always interesting. What's the scenario here?
Imagine a solid metal rod, partly submerged in mercury. The challenge is to figure out the exact temperature where the rod becomes completely submerged, assuming we can ignore the rod's own expansion for simplicity.
Okay, so as the mercury heats up, it expands and becomes less dense, right? Doesn't that affect how much of the rod is underwater?
Absolutely. It's all about buoyancy. The force pushing up on the rod depends on the density of the mercury. As the mercury gets less dense, it can support more of the rod's weight.
So it's like a race between the expanding mercury and the weight of the rod. At some point, the mercury wins, and the rod is fully submerged.
You got it. You'd use the coefficient of expansion for mercury and its initial density to figure out how the density changes with temperature. Then find the temperature where the mercury's density is just right to support the whole rod.
We're really getting into the nitty-gritty of thermal expansion now. Okay, what's next?
The source takes us on a bit of a detour with this next problem. It involves 4 glass columns connected by horizontal sections, all at different temperatures. A real thermodynamic obstacle course.
Okay, this sounds complicated. What's the point of this setup?
It's actually a really clever way to indirectly measure the coefficient of expansion of a liquid. Think about it. As the liquid in the warmer columns heats up, it expands and pushes some liquid into the colder columns.
So the liquid levels in the different columns will change. But how does that tell us about the liquid's expansion?
The key is the height difference between the liquid levels in the outer columns. That difference is directly related to how much the liquid expanded in the warmer columns.
Ah, I see. So we can measure that height difference, calculate the volume change, and then use that to figure out the coefficients of expansion. It's like working backward from the result to find the cause.
Exactly. A brilliant example of how physicists can get creative to measure these fundamental properties. Okay, ready to return to something a little more familiar? Let's take a look inside a mercury thermometer.
Wait, we're not done with thermometers yet? I thought we covered those already.
We good, but this time we're going deeper, exploring the details of its design to understand the precision involved in making it work.
Okay, so what do we need to consider besides the mercury itself expanding?
Well, the glass bulb and the capillary tube holding the mercury also expand as the temperature rises. That affects how much space the mercury has to move around.
Right, it's not just the mercury expanding, it's like the whole container is changing too. So we have to figure out how much the volume of the space for the mercury changes.
You got it. And the difference between the mercury's volume change and the container's volume change tells us how much the mercury level rises, which gives us our temperature reading.
It's amazing how much detail goes into something so seemingly simple. I never would have guessed. All right, what's next on our thermometer tour?
The source introduces a new type of thermometer, something called a weight thermometer.
A weight thermometer. How do you measure temperature with weight?
It's an indirect method that focuses on how the mass of the liquid changes as it expands or contracts. Instead of watching the volume directly, we're essentially weighing the liquid to figure out how much it's expanded.
That's pretty creative. But how does that actually work?
The key is the relationship between volume, mass, and density. The source probably gives a formula that links those things together, allowing us to calculate the coefficient of expansion based on the mass changes at different temperatures.
So we can literally weigh the liquid to figure out how much it's expanding. That's mind-blowing. But the source also mentions this coefficient of real expansion. Is that different from what we're measuring with the weight thermometer?
Good catch. The weight thermometer gives us the coefficient of apparent expansion, which is based on the observed volume change. But remember, the container itself is also expanding. The coefficient of real expansion is the true expansion of the liquid, corrected for the container's expansion.
So it's like adjusting our measurements to account for the fact that our measuring tool is also changing. It's all about precision, isn't it?
Precisely. Every little detail matters in thermodynamics. Now, how about we shift gears back to the aluminum rod? This time, the problem is about how much the rod expands when it's heated and how much energy is needed to make that happen.
Okay, so we're back to the basics of thermal expansion and heat capacity. What's the specific scenario?
Imagine an aluminum rod with known dimensions and properties. The problem is to figure out how much the temperature rises if the rod's length increases by a tiny amount, like zero point 0.3 millimeters. And then we have to calculate how much heat energy was needed to cause that temperature change.
That's a two-part challenge. First, we use the coefficient of linear expansion to connect the change in length to the change in temperature. Then we use the heat capacity to link that temperature change to the heat energy absorbed by the rod.
You've got it. A classic example of how thermal expansion and heat capacity go hand in hand. Okay, ready for something a bit more, well, submarine-y?
Submarines, now we're talking. I love where this is going.
This problem brings together buoyancy, density, and thermal expansion, all in the context of a submarine submerging in seawater.
Okay, this is definitely real-world stuff. What's the challenge?
Imagine a steel submarine that needs to take in a certain amount of water to submerge when the sea temperature is 10 degrees Celsius. The question is, how much less water does it need to take in when the sea temperature is warmer at 15 degrees Celsius?
So we had to think about how the temperature affects both the seawater and the submarine.
Exactly. The warmer seawater is less dense, so the submarine is more buoyant and needs to displace less water to sink. But the steel submarine itself also expands slightly in the warmer water, which works against the buoyancy change.
So it's like a tug of war. Which effect wins?
We need to calculate and see. We'd use the coefficients of expansion for both seawater and steel to figure out the volume changes. Then we compare how much water the submarine needs to displace at each temperature to match its weight.
I'm starting to see how all these seemingly separate concepts are actually deeply interconnected. Okay, what else is in store for us?
Let's revisit our friend the pendulum clock one last time. We know thermal expansion can mess with its accuracy, but this time the challenge is to actually calculate how much the time period changes with temperature.
So we're getting quantitative here. Sounds like a fun challenge.
It is. Remember, the time it takes for a pendulum to swing back and forth depends on its length and gravity. As the temperature rises, the pendulum expands, making it swing slower.
So even a tiny change in length can throw off the whole clock. That's why they keep those super precise clocks in climate-controlled rooms, right? To keep the temperature constant.
Exactly. To solve this problem, we'd use the formula for a pendulum's period and the coefficient of linear expansion for whatever material the pendulum is made of.
Calculate the change in length, plug it in the formula, and we get the change in time period. I'm starting to feel like a real thermodynamics pro.
Oh, okay.
What's next?
The source throws us a curveball with a more complex pendulum, one made of two different materials. This is all about differential thermal expansion.
Differential. Does that mean the two materials expand differently?
You got it. And that can cause problems if you're not careful. Imagine those two materials are joined together to make a pendulum. As the temperature changes, they might expand at different rates, messing up the pendulum's length and throwing off the clock.
So the challenge is to find the perfect combination of materials and lengths so that the expansions cancel each other out and the pendulum stays the same length no matter the temperature.
You're a natural. That's exactly it. We'd need to use those coefficients of expansion again to figure out the right balance between the two materials.
This is getting seriously challenging, but I love it.
It's all about pushing our understanding further. This deep dive has been a whirlwind tour of thermodynamics, hasn't it?
It has. I'm honestly amazed by how much we've covered. Who knew thermodynamics could be so fascinating and relevant to so many things?
It is a clever method. It uses the relationship between volume, mass, and density to get at that expansion.
Pretty neat. But the source mentions this coefficient of real expansion. Is that different from the apparent one we get from the weight thermometer?
Good point. The apparent one is just what we see happening to the volume. But the glass container itself is also expanding, right? So the real coefficient, that's the true expansion of the liquid. Like we took the container's expansion out of the equation.
So we're correcting for the fact that our measuring tool is changing too.
Yeah.
Makes sense. Okay, back to the aluminum rod I see. What's the challenge this time?
This one brings back thermal expansion and heat capacity working together. Shows how they're both part of the picture.
Okay, so we've got our aluminum rod. We know its size, density, all that. And we want to find the temperature rise if the rod gets a tiny bit longer, like 0.3 millimeters longer. Then, how much heat did that take?
2 steps. First, we got to connect that length change to the temperature change, then figure out the energy involved.
So use the coefficient of linear expansion to find the temperature change that would cause that 0.3 millimeter stretch. Then, with the rod's mass, specific heat, and that temperature change, we can calculate the heat energy needed.
Right on. It's applying those concepts in a practical way. Shows how materials react to temperature changes in the real world.
I feel like I'm getting the hang of this. Okay, what's next?
How about a problem with the submarine? This one's all about how temperature affects its ability to dive and resurface.
Submarines.
Ugh.
Cool. Sign me up.
This brings buoyancy, density, and thermal expansion together.
Sounds complex.
It is, but really interesting. Imagine a submarine made of steel that needs a certain amount of water inside it to sink when the sea is 10 degrees Celsius. How much less water would it need if the sea was warmer, like 15 degrees?
Ah, so the temperature of the water matters because it changes the density.
Exactly. Warmer water, less dense so the submarine floats more easily, needs to displace less water to sink. But TT, the steel submarine itself, also expands a bit in warmer water, which means it needs to displace more.
Wait, so it's working against itself.
Yep. We got to figure out which effect is stronger. We'd use those expansion coefficients again, for both seawater and steel, to see how much their volumes change. Then we'd compare how much water the submarine needs to displace at each temperature to sink.
I'm seeing thermal expansion everywhere now. Okay, what's our last challenge for this deep dive?
Let's go back to the pendulum clock. We talked about how heat slows it down, but now let's calculate how much slower.
So putting numbers to it, I like it.
Remember, a pendulum's swing time depends on its length. Longer pendulum, slower swing. When it heats up, it expands, messing up the clock's accuracy.
Right, so even a tiny change in length matters. That's why those fancy clocks are kept at a super steady temperature, right?
Exactly. To solve this, we use the pendulum's time period formula and the coefficient of linear expansion for its material.
So we find the change in length, plug it into the formula, and boom, we know how much slower the clock ticks. I'm feeling pretty confident about thermal expansion now. But the source mentions a pendulum made of 2 different materials. What happens then?
That's where things get tricky. It's called differential thermal expansion. If those materials expand at different rates, the pendulum's length can change unevenly as the temperature changes.
So it's like the 2 materials are fighting each other?
Kinda. To keep the clock accurate, you'd need to find the right combination of lengths and materials so their expansions balance out perfectly. No matter the temperature, the pendulum stays the same length.
That's some next-level thermodynamics thinking.
It is, and it shows how these concepts apply to real engineering problems.
Wow, this deep dive has been incredible. We've covered so much ground, from the Zeroth law to submarines to super accurate clocks. It's amazing how thermodynamics is connected to, well, everything.
It really is. From the tiniest atoms to the vastness of space, heat, and temperature are fundamental parts of our universe.
And I feel like I've gained a whole new understanding of how it all works, thanks to these excerpts and your amazing explanations.
It's been a pleasure exploring these concepts with you.
And to all our listeners, keep those brains firing and stay curious. Until next time.